Hello and welcome to Unit 1, Lecture 2 for Introduction to Logic. Today we're going to start doing symbolic logic, and we're going to start using symbols to represent components of logical forms. So we talked last time about how logical form determines the validity or invalidity of arguments. And we're going to start using mathematical-like symbols to represent elements of logical form. So that's called symbolic logic, the study of the evaluation of arguments using mathematical-like symbols. And you're probably used to symbols like the plus sign or the equal sign in math to stand for things like addition and equality. We're going to use signs like this V-shaped wedge and a wavy line, tilde, to stand for the logical concepts of disjunction and negation. These are elements of the form of arguments. I'll say more about what those concepts actually mean in a bit, but for the moment we're going to study a form of symbolic logic called sentential logic, also called propositional logic, and it's where the form of the argument is determined by how complex statements are made up of simpler statements. Those are built up something called a truth functional statement connective, and that's a mouthful, truth functional statement connective. What's a statement connective? Statement connective is a word that's used to make a complex statement out of a simpler one. Or we say molecular statements out of atomic ones. So there's an analogy there to chemistry, where we talk about molecules and atoms. And that sounds like something really complicated, but it's actually quite simple if you think about what we're actually talking about. So in English, statement connectives are words like and, or, but, if, only if, unless, not. Those are very simple words, and they represent very simple concepts, and that's what we're going to be talking about. So an atomic statement is a statement that's not made up of simpler statements. A molecular statement is a statement that has simpler statements as parts. So every molecular statement can be broken down into atomic statements, and the words used to join together or modify those atomic statements. So here are some example molecular statements. I live in Amherst and I hate living there. So the atomic statements are I live in Amherst and I hate living there, and the word and is used to join them. So and is a statement connective, and it joins together the two atomic statements to form a molecular statement. If Twilight was a good movie, then I'm crazy. So again, Twilight was a good movie and I'm crazy are the atomic statements making this up, and if then is a statement connective joining the two together. You shouldn't take this class unless you are prepared to work hard. So the simple statements making this up are you should take this class, if we modify with not, then you are prepared to work hard. We join that together with the other one with unless, and we get a molecular statement. So the atomic statements are in red, statement connectives are in blue. So in our symbolic logic, what we're going to do is we're going to use uppercase letters to represent atomic statements. And we're going to use the symbols that we learned to represent the statement connectives, which we use to join together the atomic statements to make the molecular statements. So if we take I live in Amherst and we represent I live in Amherst with L, and I hate living there as H, we might write L ampersand H. So this and sign is called an ampersand. L ampersand H to represent the molecular statement I live in Amherst and I hate living there. So L for the one atomic statement, H for the other one, and the ampersand for and. And how exactly do we understand these statement connectives as applying to logical form? Well, we're going to understand them as standing for a certain kind of function. What's a function? Well, the notion of function is probably familiar from math, but if it's not, let's talk a little bit about what we mean by a function. So a function is something that has inputs and outputs. So when we're dealing with numbers in math, a function will take a number or multiple numbers as inputs and give you a number as output. So the function square root, for example, will take 4 as input and give you 2 as output. So that 4 goes into the function and 2 comes out. The addition function has 2 inputs. If it takes 5 and 7 as its inputs, it yields 12 as its output. So the inputs are called the argument and the output's called the value. Now those are when we deal with functions that deal with numbers. In logic, we don't deal with numbers, we deal with truth and falsity. So our functions are actually simpler because rather than taking the infinite number of different numbers as possible inputs and outputs, our inputs are just truth and falsity. Call these the truth values of statements, truth and falsity. So a statement connective in sequential logic can be understood as a truth function. So what that means is that we take the truth or falsity of the simpler atomic statements as inputs, and then we calculate the truth or falsity of the molecular statement depending upon the input of the atomic statements, right? So suppose that we are dealing with an and statement. Amherst is in Massachusetts and Boston is in Massachusetts. If both of those are true, which they are, you can think of the two inputs going into the function as both true. When the two inputs that go into the function that and represents are both true, the output is also true. The and statement, the entire complex statement, is also true when both of the two sides are true. But when one of the two sides is false, like when I say Amherst is in Massachusetts and Chicago is in Massachusetts, the output is false. So we'd write that in symbolic logic. We'd write the first one as A ampersand B, and we regard that as true. We might write the second one as A ampersand C, Amherst is in Massachusetts, Chicago is in Massachusetts, and we regard that as false. So when both inputs are true, the output is true. When one of the inputs is false, or they're both false, the output is false. So that gives you the basic idea of how truth and falsity come in as inputs, and truth or falsity come out as outputs. Right? So today we're going to represent 5 different truth functions, and we'll represent symbols. We use symbols to represent those truth functions. So the first one I'm going to talk about, the next one we'll talk about is negation. And that translates the word not. So we write this as a wavy line called a tilde. And we write it before what's applied to. So if A is some statement, I should say that when I use a fancy cursive A like I am here, that's any statement, simple or complex. A could already be complex. If I take A and it's true, and I put not on it, if I take something true and I say not before it, I end up saying something false, right? If I say today is Tuesday and it's not, sorry, today is Tuesday, and then I say it's not Tuesday, then I'm saying something false. If today is Tuesday, if that's false, and I say it's not Tuesday, I say something true. So negation will take the input, the truth or falsity of the input, and reverse it. If I take something true and I say it's not the case, I say something false. If I take something false and I say it's not the case, I say something true. So this wavy line represents not, or the phrase it's not true that, or the phrase it's false that, or it's not the case that. Other logic books use other signs. Some of them use a little straight line, which looks like a negative sign for math. Some of them use a straight line with a little hook at the end. And we're going to use this wavy line called a tilde. And even though some books use a negation sign, don't think of this as the concept of negative. To say I'm not 8 feet tall is not the same as to say I'm negative 8 feet tall. I don't know what it would mean to say that I'm negative 8 feet tall. Again, this is a truth function. So we take the truth or falsity of the input and we reverse it, and we add the word not. Okay? So the next one we're going to talk about is called conjunction. We've kind of already talked about this. This is what the notion of and represents. Unlike negation, it has 2 inputs. Negation just has 1 input and reverses the truth or falsity of the input. Conjunction is written with the ampersand sign. You probably already know this sign. We write it in between the 2 things it connects. The 2 things it connects are called the conjuncts of the conjunction. So conjunction is made up of 2 parts that we call the conjuncts. Now, since there are 2 inputs, there are 4 possible combinations for the 2 inputs. So I take A as one conjunct and B as the other conjunct, and I form the conjunction A ampersand B, A and B. If A and B are both true, the conjunction is true. If A is true but B is false, if one of the 2 sides is false, the conjunction is false. So when A is true and B is false, but also when A is false and B is true, what I say is false. If they're both false, I'm still saying something false. If I say 2 false things and I join them together with and, I'm still saying something false. So this translates the word and, but also the words but, moreover, however, although, yet. That might seem like and but mean something different, but they actually only have a different in connotation, not in exactly what they mean. I'll talk more about that next week or in a week or 2. I don't know exactly where I'll get to it, but we'll talk more about that later on. Some other logic books use different signs for conjunction. Some of them use a dot, some use an upside down V, but we're going to use the ampersand sign that you're already familiar with to represent the notion of and, also called conjunction. Next one we're going to talk about is disjunction, or, which which we represent with a little wedge-shaped sign called the, which also looks like the letter V, lowercase letter V. We call that sign a wedge, and it forms what we call a disjunction. That's a fancy word for or. The two inputs to this junction are called the disjuncts. Now, if I take A and I take B and they're both true, we regard A or B as true. When A is true and B is false, we still regard that as true. When A is false and B is true, we regard that as true. It's only false when both sides are false, right? So if I take two things and I say either this or that, if either of the two sides is true or they're both true, regarded as true. Now, it's arguable that in English the word or is ambiguous. Some people think that sometimes or, when both sides are true, can sometimes be false. That's called the exclusive or. But our wedge sign is the inclusive or. When both sides are true, we're going to regard it as true. So if I say either the Yankees will be AL champs or the Mets will be NL champs, those could both be true, and I still would regard that sentence as true if both end up being true. Or if I say either the Red Sox will be AL champs or the Yankees will be, those can't both be true. Now, it's a little bit controversial whether that's part of the meaning of the sentence, if they're not both true or not. If it's part of the meaning of the sentence, then we wouldn't translate that just using the wedge sign. We use a more complicated translation. But our or is going to be the inclusive or. If both sides are true, we're regarded as true. Okay. The next one is probably the most complicated one of the five we're going to be talking about today. It's written as an arrow, and it's called material implication, also called the material conditional. And it's kind of like an if-then, but not exactly an if-then. So A arrow B, if A and B are both true, we regard A arrow B as true. When A is true and B is false, we regard A arrow B as false. When A is false and B is true, though, we regard it as true. So the order matters. We got true on the left and false on the right, it's false. When we got false on the left and true on the right, it's true. When A and B are both false, we regard it as true. So it rules out the A part being true and the B part being false. It's false if that's the case. So it's only true when that's not the case. We don't have true on the left and false on the right. So if the left part's true, then the right part has to be true as well. Right? So it's kind of like an if-then. We regard the if part, what comes before the arrow, is called the antecedent, and the part that comes after the arrow is called the consequent. That's consequent with a T, not consequence. Other logic books will use either a horseshoe-shaped sign for this or a different-looking arrow. But we're going to use a regular arrow for the material implication. Now, we're going to use this to translate if-then or only if or implies that, but it's a truth function, so all it cares about is the truth or falsity of the inputs. Now, the phrase if-then in English probably isn't actually a truth function. It probably does care about there being a link between the two parts. It's not just about whether they're true or false, it's about whether there's a link between them. So to illustrate the difference between if-then in English and our arrow, I'm going to give some examples. So with the arrow, we regard an arrow statement always as true when the part before the arrow is false. Now, it doesn't quite seem to be how if-then works in English. So to say if Mitt Romney is the president, then a Democrat is running the country. Now, Mitt Romney, if you don't know, was a Republican. So probably doesn't seem true to say this, right? But if we look at the parts, Mitt Romney as president is false. A Democrat running the country is also false. False, arrow, false is true. If we write this with an arrow, we're going to regard this as true, because we just care about the inputs. If we have false on both sides, we're going to regard that as true. Similarly, if the thing that comes after the arrow is true, it doesn't matter what's happening before the arrow. If both sides are true, or if we have false on the left and true on the right, we're going to regard that as true. So I say something like this: if Kevin grew up in Milwaukee and Kevin lived in Minnesota, I'm talking about myself here. I did grow up in Milwaukee and I did live in Minnesota, but of course those are different parts of my life. Milwaukee is not in Minnesota. It doesn't really seem like there's a right link between these. It doesn't really seem like that's true. But since both the atomic parts are true, we regard this as a true statement. We're going to regard this as true. So the arrow is not exactly the same as if-then, but the closest we can come to translating the arrow into English is if-then. So that's how I'm going to read this. When we have true on the left and true on the right, we regard this as true. Now, it might seem strange that we have false on the left and true on the right, regard this as true. But if I were to say something like, if it's October, then it's autumn, right? It's false if it's October, it's true that it's autumn, that still seems true. So we can have statements like that we regard as true. Only time we regard this as false, we have true on the left and false on the right. Okay? And the last of the truth functions we're going to talk about is material equivalence, also called the material biconditional. Now this is like the one-way arrow, but it's a two-way arrow. The arrow goes in both directions. The sign is called the double arrow. Regard this as true when the two sides are the same. So when A and B are both true, it's true. When A and B are both false, we regard it as true. When we have true on the left and false on the right, we regard it as false. When we have false on the left and true on the right, we regard it as false. So we use this to translate the phrase if and only if, or the abbreviation of if and only if, you may know from math, IFF, or the phrase just in case. So the two sides have to be the same, right? But again, this is a truth function, so all it cares about is the truth or falsity of the inputs. It doesn't care if there's a conceptual or cause-effect link between the two. If I say Hillary Clinton is president if and only if Bernie Sanders is president, that seems false. But both sides of that atomic or molecular statement, both the atomic statements making it up, are false. So false, double arrow, false, we're going to regard as true. So we're going to write this with a two-way arrow, we're going to regard this as true. So other books use like a funny shaped equal sign that uses 3 bars rather than 2 bars for material equivalence. We're going to use the two-way arrow for material equivalence. Okay. So we're going to use these signs to form molecular statements out of atomic statements, and we can form them using more than 2 atomic parts. We can combine them together, just like you can take a plus sign and then take the result of that addition and then subtract something from it. You can take a disjunction and then take that disjunction and make a conjunction with that disjunction, right? That happens in this example. The election was held on November 7th, 2000, and neither Bush won the election nor Gore won the election. I write that as E ampersand in parentheses B or G. I can also say this: if you think NSYNC was good or you think the Backstreet Boys were talented, then you're crazy. If, in parentheses, N or B, N represents you think NSYNC was good, B represents you think the Backstreet Boys were talented. If either of those, then C, where C means you're crazy. I hate Justin Timberlake, H, but, that's ampersand. If you like Fergie, that's L. Then, if, another if you don't like Britney Spears, not B, then we can still be friends, F. H and, in brackets, if L, then if not B, then F, right? So to translate these, we're going to use multiple symbols, multiple signs. The first one we use an ampersand and an or. The second one we use an or and an arrow. And the last one we use the ampersand and 2 arrows, and also a not sign for the int on you do like Britney Spears. And we need parentheses here. So the parentheses are there for the same reason we need parentheses in math. The order in which we place the parentheses determines the order in which we calculate the truth functions that determine the truth or falsity of the molecular statements. But just like in math, the order of the parentheses can matter. If I say in parentheses 12 divided by 3 divided by 4, I do the 12 divided by 3 first. 12 divided by 3 is 4. 4 divided by 4 is 1. That's different than if I do 12 divided by, in parentheses, 3 divided by 4. 3 divided by 4 is 3/4. 12 divided by 3/4 is 16. That's a very different result. If I make A, B, and C true and X, Y, and Z false, I'm just assuming that for the moment, we get different results here. A or B ampersand Y, where A or B is in parentheses. A or B, both sides are true, it's true, but true and false is false. That's false. But if I say A or in parentheses B ampersand Y, we do the B ampersand Y first. True and false is false. True or false is true, though, so that would be true, right? So the order in which we apply these truth functions makes a difference to the result. I should say when we apply negation, negation only applies to what comes immediately after it. If we want to make negation apply to something complex, we've got to use parentheses. So if I say not Y or C, the not just applied to the Y. So Y is false, not Y is true. True or true is true. But if I have Y or C first, that's false or true. False or true is true, but then I apply the not, I get something false. So the order in which I apply that negation, what I apply that negation to, changes the truth or falsity of the statement. So you always work from inside the parentheses outwards when you're calculating the truth or falsity of a statement. Negation only applies to what comes immediately after the negation. So if there's a negation and something else inside the same number of parentheses, you do the negation first. So you calculate the negation before you calculate anything inside the same number of parentheses. Okay? So let's look at some examples of this. B and C, we do that in parentheses. True and true is true. Not A, we're going to do the not before we do the wedge because it's inside the same number of parentheses. So not A is, since A is true, not A is false. False or true is true. The last thing I calculated there was the or. We have a special name, I say this down here, called the main connective or the main operator for the last thing you calculate. That's the glue holding the entire statement together. The glue holding the entire statement together for this first example is the wedge, the or sign. The and only applies to the B and C, but the or, as it were, glues the entire statement together. We call that the main connective. All right, let's do number 2 here. So remember in this parentheses, false or false is false. Then we do the negation, that's true. Now let's do what's on the other side here. True double arrow false is false. True and false is false. So this entire statement is false. The main connective is the and. That's the glue holding the entire statement together. All right, let's do this next one. So we have to do what's inside the 2 parentheses before we do what's inside the brackets here. So A or Y, true or false is true. True arrow true is true. Then we do the negation. That makes it false. False arrow false is true. The main connective, the last thing we did was the second arrow. The arrow that comes after the brackets. That's the last thing we did. All right, so let's do this one. Pretty complicated. We work inside the double parentheses first. We'll start with the A. We do these negations first. So A is true, not A is false, not A. The double negations cancel each other out, so not A is true. True or true is true. And we have a negation applied to that. That's false. False and true is false. But then we have this first negation, makes the whole thing true. The main connective, the last thing we did is this first negation that's applied to everything in the brackets. That's the main operator that's applied to the entire thing. So the first negation is the main operator. A or not A. A is true, not A is false. So true or false is true. The main connective is the or. Now it's funny, this looks, 5 and 6 look exactly the same, except we start with something true in this one, and we have something false in this one. False or not false is true. False or true is true. So it doesn't matter which thing we do. If we have a statement of that form, we get something true. We'll talk more about how that's important in the next one, our next lecture. The main connective again is the or. All right, so you have some homework where you have to do these calculations. Hopefully it's clear enough how you do that, and I'll catch you in the next one.